Welcome. So, in this lecture I want to present MATLAB demonstration of Simulink model development as well as simulation of switch mode power converter. So, what are the topics that I am going to cover is that first introduction to MATLAB simulation, then introduction to different blocks of Simulink like source, sink, dynamics and arithmetic and logic operation, then development of Simulink model for various switch mode power converter, particularly buck converter, boost converter that we did. In fact, we can develop isolated converter, various type of converter that you can plug in into the Simulink. So, we will develop from the scratch, and whatever equation we have written, that we want to actually create the Simulink model for those mathematical block diagram. Syncing then with MATLAB coding and Simulink, that means synchronizing MATLAB code and Simulink, and finally, I will also show how to process data. That means, if we see the scope simulation result which does not look good, we need to take those data into the workspace, and then from the workspace we need to plot it, and we have to create according to this axis command, and then we will show some case study simulation. So, first circuit that we are going to consider is the series RLC circuit. In this circuit, we know we have in the previous lecture we have already implemented that develop the model along with the block diagram, and this one we are going to make the Simulink model for this particular series RLC circuit. So, what is necessary? So, whenever we try to develop the Simulink model, there are certain parameters. For example, we have this resistance, we have this 1 by L, we need 1 by C, we also need the source. Then we need to set, as I said earlier, we need to set the initial condition of the current here, and we need to set the initial condition of the voltage here. So, all this part we need to plug in, we need to put this information in order to run the simulation, and in the Simulink model we will plug in those parameters instead of putting values, so that we can change the parameters separately using a script file. So, what we have to do? We need to create a separate script file which is a .m file, where we will define all the parameter, the notation that we are using here, and we need to use a consistent parameter symbol, otherwise it will give error. That means, whatever symbol we will use in the Simulink, the same symbol we have to define in the .m file, and then we need to specify the value of that particular let us say for the inductance value, we need to give what is the value of the inductance, what is the value of the capacitor. So, with this we are going to start. Now, in the first one I will tell you .m file, I will go to that. So, suppose I choose an inductance, and if I do not specify, these are the command file. So, it does not matter, it will not be executed, but these are the file which will be executed. So, when in the MATLAB we will only give values. So, values means inductors, it will be considered in Henry, capacitor in Farad, resistance in ohm, and current in ampere and voltage in volt. And if we want 2 microhenry inductor, so that means we have chosen here L equal to 2 microhenry. So, this can be written as 2 into 10 to the power minus 6 Henry, and in MATLAB we simply write 2e minus 6, and we do not need to give it, that means it is Henry. So, we need to just specify the values here. So, this is the inductance value. Similarly, for this one capacitor, this is like a 100 microfarad capacitor, and here we are considering load resistance to the 1 ohm. So, we can choose any other resistance value for the simulation. Now, this block actually now this is a parameter block. So, this has to be created as a .m file, script file, and which extension file is simply .m file. Now, let us go to the Simulink block and we will see how do we implement this block. So, here initially I will open, whenever I will open the MATLAB block simulation, you need to set the specific location where you want to keep your simulation file. So, here this is a path that I have created for this particular case study, and do not bother about this file. So, here I need to create a new script file. This is the new script file, and let us say I put a inductance value L equal to 2 e minus 6. That means, this is a inductance is equal to 2 microhenry. I want to use capacitor to be, let us say 100 e minus 6, this is 100 microfarad. Then I want to use resistance in this case equal to 1 ohm. Since we are not putting any symbol, it will be treated as L into L in terms of Henry, C in terms of capacitor in farad, and R in terms of resistance in ohm. So, the same thing I can save. So, I have created a file just to give you an intuition. Okay. Now, I need to save this file somewhere. Let us say this is a parameter file, parameter for the series RLC. You can define your own parameter file, but these three are not sufficient, because what else are needed in our simulation? We also need the initial values of this, and we discussed we need to define the initial value of the inductor current and the initial value of the capacitor voltage. So, this initial value we can initialize, like we are talking about IL 0, this can be treated as initial value. Let us say this we take directly as a 0. Similarly, I need to take capacitor initial value. You can define your own initial notation, but it has to be consistent 0. Okay. Now, this actually generate all these simulation files, and we need to keep this simulation file in the backup, and we have to run it. Now, what is our next task? So, we need to develop a Simulink model. Okay. So, we need to create a new file. So, this file Simulink, that means okay. So, we need to create a Simulink file. Let me check where is the Simulink block. Here, yeah, this is a Simulink. So, if you go to the home page of the MATLAB, then you will see the Simulink tab. So, it depends upon the version of the MATLAB that you are using, and if we open that, then it should open a Simulink file. Okay. So, you open a new simulation file. This is a Simulink library. Let us open a simulation file. So, I am just removing all this block from here. Created, this is a simulation file, new Simulink file, and in this Simulink file we want to build up the model that we discussed. So, if we go to the previous simulation in this model, first we need to create this inductor current block, then we need to create the capacitor voltage, that path, and then we have to combine this whole equation. Let us go and create. So, in this simulation, if you go to library, there are commonly used blocks, and we will use most of the blocks from here, commonly used. The first block we need is the integrator, because this block is needed. What is the purpose of this block? This block is to generate the current and voltage. Just a minute. Yeah. So, this is my integrator block. I can call it as a IL, because this block will set the initial condition also. and here the initial condition that we want to set, you should take it, it must be consistent. So, this we should copy from the .m file and you set it here as a .m file. So, the same must be used. Now, we want to generate another such block, we need to copy and paste Ctrl C and Ctrl V, and here it is V C 0, because this is, and again we can go and use this initial block and we should use this block. Now, we have placed two, one for inductor current, other for capacitor voltage. What is next? So, that means the right side of this block is the inductor current and the left side of this block is DIL dt, right. And what is DIL dt? We have DIL dt, if we multiply it with 1 by L, then we will get VL, inductor voltage. So, we need another block, okay, Simulink library. So, here we need something like a gain block, gain. So, gain block, this gain block will set 1 by L, 1 by L, and this 1 by L, now it is a parameter. Similarly, we can copy paste this block and this block is used for 1 by C for the capacitor. And I am just referring to our presentation, that means this is the 1 by L block, because I am talking about this 1 by L block, and this is 1 by C block, it is multiplied by 1 by S, that is my integrator. Okay. Next part, that we need to use an adder block, that means go back, one summing block should be, we need it, and this summing block, what we need to add, you know, for this series RLC circuit, we need to, this side of this terminal is my inductance voltage. For a series RLC circuit, what is the inductor voltage? That is, because it is the input voltage minus the voltage across resistance minus the capacitor voltage. Okay. That means, we need plus minus minus. Okay. So, since we want to connect minus plus minus, okay, this is for just notational simplification, we will join this block. Now, again we want to create a block. If we rotate, this block is resistance block, this will use with this block and it will be this. So, what is this? If we go back to our presentation, this is my resistance block. So, I am talking about this block, which will be multiplied with the current and subtracted from the this, it will be subtracted. Okay. Similarly, we need to subtract the capacitor voltage, that means I am talking about this terminal, this particular terminal. So, once I go back, then we need to subtract this voltage here. Okay. All right. That means we now, then what is left? What is left is the my supply. Okay. So, I can take a source. If you go to source, there are various type of source. In the Simulink library, if you go to source, there are various type of source. So, let us say I choose a pulse generator, that means I want to give a DC for short time, then 0. So, repeated pulses. You can generate any other signal also, you can generate a sine wave AC, you can generate DC, even you can put a custom blocks for simulation, that is also possible. So, we will slowly move into more complex block, but we will start with a simple block. So, in this block we want to apply a 10 volt DC, amplitude of 10 volt, with a time period of 1 millisecond, 1 e minus 3, and 50% duty ratio. That means, we want to apply what we want to apply. That means, we want to apply a pulse which width is 50%, and during 50% time the signal, the voltage will be 10 volt, then remaining 50% time it will be 0 volt. So, it will vary from 10 to 0 and with a time period of 1 millisecond, that we said. Okay. The next block, if we go back, is the capacitor voltage, which is, if we multiply by 1 by C, that is already there, that is my capacitor current. So, this terminal is my capacitor current. So, this is my capacitor current, and in this case the capacitor current is same as the inductor current, because it is flowing through this path only, series path. So, in the Simulink, I will simply connect this block with this block, with this, in this block, simply connect this block. That means, now we have defined 1 by L, we have defined 1 by C, we have defined resistance, we have defined initial condition, we have defined this initial condition. Okay. And here we want to set the simulation for maybe 2 microsecond to 2 milliseconds, sorry, but we want to display the waveform. In order to display the waveform, we have to go back and sync block, where you will find a scope. There are various type of scope. One scope is here, a simple normal scope, like which will show the time domain signal. If we double click on the scope and go back to the scope, in the setting block, here you will get a setting block, where you can select 2 axes, even you can select 3 axes, whatever you want, and in that axis, I think in this axis, yeah. So, this is my axis. I am just considering 2 axes. Histogram, I do not want to limit the data, because histogram is that the final 5000 data point it will display, but that we do not want. I want to show the complete simulation, because sometimes this history block help in order to, because if you want to display each and every data, then the simulation can take long time, longer duration. But if you want to speed up simulation, we want to show some final data point. So, this is used for limiting data, but here we are not using, we are not limiting data. But what we want to save the data result, scope result into workspace. So, I have to select this workspace, and I can define the custom. Let us say I am just defining something called result block, and I will structure with time. So, it will show something like this scope. If you go to Simulink, I will show you. So, this is the block that we have already made, and I have to add this particular block in the scope. Okay. So, now in the scope, what are we going to show? The first signal that we want to show is the current in the inductor current. The second signal we want to show is the voltage across the capacitor, and the third signal we want to show is the input voltage, how the input voltage is varied. Now, we are all set, we saved it, and this is exactly what I have shown, the snapshot, a screenshot of the Simulink block. Okay. Here, in order to make it more convenient, let us put, you can always put a unity gain block, which is just to, okay. So, these blocks can help to, just a minute. Yeah. So, I can put this block here, simply here. Okay. Similarly, I can put another block here like this. block here. This is just to connect this block, and I can take everything out of this. Okay. So, I can connect this block from directly from here. Okay. This is for convenience, that is it. Now, we are ready to run the MATLAB, and this is what I have shown here. So, this particular block is to indicate, that means this signal I am showing IL. So, I can specifically write this is my inductor current, and this block I am showing is the capacitor voltage in this case. Now, I am ready to run the simulation. So, it shows some error where the initial blocks are not defined. So, undefined, that means I need to run this initialization file. So, let us go and run this file. You need to run this file. Once you run this file, these initial values are now defined, it is placed in your workspace, and then you can start the simulation, and then there will be no error. Now, you will not find any error, and it will show that means initially we are applying 10 volt for 0.5 millisecond, then because we are putting 50% duty ratio. So, it is a periodic pulse between 0 to 1 millisecond, you can see, and for 50% time it is 10 volt, then it is 0 volt, 10 volt, 0 volt, and so on. And first one is the inductor current, the second one is the output voltage. And I have also provided a snapshot, that means if you show the scope, whatever I said, the how to store the data result, and please remember in the scope, if you go to the scope history, it should be structured with time, because I want to plot this signal. Now, I will show you the data that I have plotted actually is stored here. If you go to result, this is where we put the scope data. The result block, if we go to the result block, then you will see the result time is something called result.time. You can see here result.time, it gives you all the time series data. That means, I can write here, I am creating, that means t equal to result dot time. So, it will give my time series data. So, this time series data is now coming here. So, it is like a 23,811 into 1, it is also 23,800. So, it is a double, that means it is a vector which has how many elements? 23,811 number of data are there, which are placed in a column matrix, one column like a 23,811 number of rows and one column. Now, I am interested to see what are the access data. So, these are the signal, and since signals means the scope input, because scope there are 3 inputs are there in the scope. If you see, the scopes have 3 input, but scope, in order to display each input, we need to also plot the time data, that means at different time instant what are the values of different signals. So, the time vector we have already stored. Now, in the signal, if we go to this signals, that means result dot signals, it has 3 different channel, that means 1, 2, 3. These are the 3 input. The first input is this, second input is this, and third input is this. And if we click on this first input, then it will show result dot signals this value. So, this particular thing, that means we can store like x equal to result dot signals 1 dot values. It stored the x axis data, you can see x axis data are stored. I can do it for the y axis, that means channel 2, I can create a variable like y, but interestingly you will see y, and I can also create another data for z, 3, that is in the third input, that is a z. So, now we got all the data here and we are ready to plot. So, we have time series data vector, and you see the number of element in T vector are same as x, y, z, because the number of time instant and their corresponding value, they must be consistent. Now, plot t comma x, it will show my time domain waveform of inductor current, and in this particular case now I want to see the voltage and current together. That means, instead of creating a separate figure, I want to show sub figure. So, you can show sub figure as subplot. I want to create a subplot of 2, 1, 1. That means, it will show in terms of 2 row. First row, it will show the plot which we want, and this case we want to show the plot of t on axis. I need to hold on, and we can also grid it. That means, it will show the grid. So, it will show grid. Next, we can repeat the same. We can do subplot 2, that means the second one. If we go to the second one, then we can repeat it. Now, we are plotting the voltage, and we can again hold on. That means, if you want to put another plot, it is also possible. By that way, we got the second plot. So, the first one is the current and the second one is the voltage. Now, after we complete the plot comments, it is not clearly visible. So, we can put x level as the time, it is in second, because in this it is 10 to the power minus 3 is there. Then if we select that particular channel, that means this plot, then we can insert the y level, which is my output or the capacitor voltage, capacitor voltage, it is in V. And for this plot, we can also plot y, which is inductor current. So, now we want to go to the export setup, where we can increase the font size. I want to increase to 30, and it is better to use a Times New Roman. In fact, Times will be enough. Then line width I want to increase to 2, then apply. If we apply, now the width has increased. Now, we want to, if you want to further increase, we can select, right click, you can change color if you want, let us say red color waveform. In fact, if you want to increase the line width, line style, everything is possible. So, line width, line color, anything that we want, we can increase it. Okay. So, by that way we can actually change this particular plot. So, these are the plot command that is used for simulation purpose. Okay, time series data. That means, what we learned now, if we go back, this is my series RLC circuit. Now, I can develop a parallel RLC circuit. Now, since we already know how to develop model, so we will directly go into parallel RLC circuit. What is there in the parallel RLC circuit? That means, let me go back to the Simulink file. So, series block we have implemented, this is the plot I am showing. So, I have given some plot command. So, in order to make life simple, you can create a separate file. That means, whatever I have done here, I have created a separate file in order to help, that means simulation, the result.time, result.signal. So, first one is the inductor current, second one is the output voltage, and third one is the input voltage, and you can do subplot, then figure, all this you can, if you just simply click, it will be enough, it will plot. So, this separate file is used for simulation purpose, and which I have shown in this particular data processing part. The next part we want to implement parallel RLC circuit, and this part using this Simulink block, and once we develop. So, before we go to the parallel RLC circuit, we need to now create a subsystem, because suppose we want to connect multiple such series circuit in parallel or in series. So, we can create a subsystem. So, how do you create a subsystem? That means, if you select that particular block and if you right click, create subsystem, and if you go inside the subsystem, all our block will be there, it will be retained. Here we will name it, the first block will name it as a V capacitor, that is my capacitor voltage. Okay. Oh, this block already exists. So, now I can, okay. So, I will name like a VC. Okay. This block, let us say some V, and this block I, because there will be no confusion. So, this is output port I L, and this block is my input V in. Once we go back, now it will show my subsystem, and you can name it as a series RLC. So, this is series RLC circuit. Now, if you want to create, if you want to place another series RLC circuit in series or parallel, it is possible. I can show you in the next block, but this block is now ready for use. So, now you want to show the next block, which is a parallel RLC circuit. Okay. So, that means subsystem creation is simple, and if we create subsystem, it will make my simulation easy, and it is more portable, because I want to do it for different blocks and so on. So, in this particular presentation, my aim was to just introduce the MATLAB, and we have implemented a series RLC block, which is very simple, but in the next presentation I want to build up other model of the converter, so that it will help whatever we do, whatever we learn, it will help to do a MATLAB simulation, custom building block. So, thank you very much. I think we will go to the next presentation.